Thank you, Oliver. I'm here with my boss and son, Scott Veirs, back there, and we are part of Orca Sound and Beam Reach. And I liked your initial timeline because when Scott was in high school, I was on the sabbatical on faculty at Yale doing expert systems, which was the early version of machine learning / the end of the first phase of AI. And then about 2 or 3 years ago, you and Fabio showed up on the scene and kind of knew I've got to get back into this thing after being out of it for 30 years. And so here I am. The part I'm interested in is one of the many little flowers that Fabio sort of pointed us to, the many ways to try to precondition and analyze sounds in ways that might be helpful in trying to help the whales. And the part I'm working on is trying to be more general than the specifics of each individual annotated call. I've believed for a long time, and it may well be that Paul's going to find it first by looking carefully at these wiggles in one of the beautiful flowers down there. Those lines you see on the screen are the edges of a flower. They're the contours of the spectrogram. They're the tonalities. They're what we really hear and listen to. They're the beauty of the calls. And the subtle changes in those, I think, are likely to be where the content of the calls may be, because no one's ever correlated behavior with any one of the standard S1, S19, and so on. So, a little tiny bit on preconditioning. After a talk at the ASA 6 months ago, Oliver said, 256. So I said, okay, I'm going to go back and do 256. So my spectrograms are now 256 by 256. And I do a bunch of preconditioning. This is just to show you what we see when we look at them on the screen. But this is what the algorithm in the machine learning sees. They see it in grayscale. By adding color to it, you add 3 channels that aren't really there, giving you more data, but there isn't anything unusual about that data. There's nothing more about those 3 colors than there is in just the value from the darkest black to the whitest white. So I believe I'm looking at black and white spectrograms, and I normalize them, which means I've lost any idea of how loud they are. They get normalized to the structure of those, of whatever the noise and or signal may be. I normalize them to 1, and then I square them. If you square things, strange things happen. So if you square 0.5, what do you get? It's a test. And then the answer. 0.25. So this takes lower peaks and makes them lower. It brings out the higher peaks. And that's what you see here from a spectrogram to a normalized spectrogram to one that's squared. So that's kind of one thing that I've been doing, trying to get sharper signals to go into these things. And then the other thing I'm doing is building an autoencoder. And an autoencoder is trying to work on this problem that there are patterns within these calls that may be more general than the specifics of each individual call. And the basic idea is you take a call, you grid it to a size, and Oliver told me 256, so I do it 250.
I'm pretty careful what I say from now on.
And you get some complicated way to take that 256 by 256 pixels, that's 64K, and turn it into something that's only 2K. And you say, okay, that's got to be just lost everything. You know, you've divided the information by a factor of 30. So there can't be anything left here. And then you ask the neural net, say, well, okay, there's hardly anything in there, but I want you to take that and make the input. So this is how you're training. You don't need any experts anymore, which is what we were doing at Yale decades ago. You take the input spectrogram and the output spectrogram, and you tell the computer, make it teeny tiny, and then try to get it back. In doing so, we hope, we pray, actually, that there's something encoded in there that is more general than the specifics of the individual samples. And in this TensorFlow world that these characters introduce me to, And if I can get this thing to scroll. Oh, I see. I had it. Yeah. You can write something really simple. This doesn't look simple to you, but we're down in the weeds of machine learning. It involves this convolution thing. It's not very much. Anybody can write that, especially if you go to Meridian and Petos and you kind of learn a little bit, which I've been trying to do for the last 2 years. And with that, something more complicated happens. Oh my God, this happens. I'm getting complicated stuff here too. Where is this now? So from that little bit of code, we've built a complicated thing. And it's very complicated. It's got 400,000 parameters. And then we ask it, will you take those parameters and adjust them to try to make the input look like the output? So here's the input. We run it through this complicated thing and it comes out looking like that. And near distance, they probably look exactly the same. They're actually remarkably close. I've marveled at this when I sort of stumbled into it last fall. How could it do that? And this is the visualization of the information needed by the neural net to reconstruct the input. And this one I'm showing you did this strange thing to me that it just blanked out that spot for all possible calls. I've been trying to enforce something called sparseness, and sparseness just quenched whatever that was, it went to 0. So this is a call, and this is background. And you can see it can capture both of those sorts of things. So that, I thought that was kind of interesting. And the next question after you have that, you should say, well, can we classify signals based not on the incoming 256, 64K array, but on this funny little thing that's in the middle, which is only 2,000 numbers. And we build a convolutional neural net for this subject that goes all the way down to 1 pixel, which is 1, it's a whale, 0, it's not a whale. So that's the simplest thing you could do, a binary classifier. And I built 10 or 15 of these filling around to see if I could get what would happen. And this one is one that I'm currently working on. This shows the way the model responds. They do start training it. The loss goes down, the accuracy goes up. And after letting it run overnight, it really has figured out the samples that I've given it. You'll see that there are no false positives, no false negatives on the training data. But when you give it data it's never seen before, there's 8 and 10% false positives and false negatives there. And you're thinking, well, that's interesting. What are those things? And so that's kind of what I'm working on right now. And so let's just take a look at this one. This is a false positive, not a pink one. And the little arrows up there show that the 0 is the annotator, said there's no call here. And here the classifier comes up with a number of 0.7. Well, that's pretty close to 1, so that's probably reasonable to call that a false positive. It's sort of always confusing, the false positive, false negative. If you look at it, the 0 says the annotator says there's no call. The classifier says there is a call. Well, there's a little difference between the output of the spectrogram through this neural net thing compared to the input. It's created some extra noise there. Why? I have no idea. This is what we're trying to learn a little bit about. This one is one where the annotator made a mistake, because this pretty clearly is a call. And I went and looked at the wave file and listened to it. Yeah, it is a call. So the annotator made a mistake, but the neural net has a 1 up there saying, I think that's a call. So I just had to go slap the hand of the annotator. Well, that was me, so okay. I just missed that one going through, but I'm starting to take this algorithm and run it through the wave files that I've used for training and then wave files that we've not used, but there's still more work to be done. Here's one which is a false negative, where the annotator said it was a call, it looks like a call, but the algorithm said, no, it's not a call. So that's one that has to go back into the training loop and be trained, saying, no, that wasn't a good idea. And then you get to what you do with it. So what I do with this is I'm updating the expert layer labels using the looking at each one and playing them if I have to. And then saying, yes, this one really is a call, but the annotator didn't label it properly, or this one is not a call and the algorithm made a mistake. And so I'm now working on improving the training database, and I just started to unleash it on totally independent data, and I'm aiming toward, as I have started 2 years ago with first master guys, getting it all run on a little tiny thing called a Jetson Nano, which is a little tiny special edge processor, so that we could have something running as a detector at the ultrasound node. So that's kind of where this project stands.
Thanks, Al.